We live inside a mind that evolved for nearby things. For most of human history, large meant a mountain on the horizon, a storm front rolling in, a whale breaking the surface. Our senses became skilled at judging what could be walked to, held, escaped, or returned from. But the universe does not stay within those distances. Out beyond the reach of touch, scale becomes a different kind of problem, one that isn't solved by sharper eyes, but by new ways of thinking. A black hole is the clearest example of that failure. It is not an object we can look at in the usual way. It offers no surface, no light, no reassuring outline. And yet we speak about some of them as largest, as if size were obvious, as if measurement were simple. To call something the largest black hole we've ever measured is to make a quiet claim about knowledge itself, that a mind built for firelight and footsteps can still reach into regions where space is bent, time is uneven, and the usual meaning of seeing begins to dissolve. This journey is about that claim, what we mean by largest, what we mean by measured, and what must be true for us to say either with a straight face, starting with the deceptively simple question of what a black hole is, before we ever try to weigh one. A word like largest feels simple until it meets something that refuses to be outlined. In ordinary life, size is a boundary you can trace. It is a doorframe you can stand in, a shoreline you can follow, the edge of a shadow on a wall. Even when we cannot measure precisely, our eyes and hands agree on where an object stops and everything else begins. With a black hole, that agreement is missing. There is no surface to shine light from, no texture to catch a glint, no final layer where matter rests and stays. There is only a region of space where the rules of escape change. So when we say the largest black hole we've ever measured, we are already choosing a definition before we ever choose a number. We are deciding what largest is allowed to mean in a universe where the most important objects may be defined by absence. The closest thing a black hole has to an edge is not made of material. It is made of consequence. It is a boundary drawn by motion itself, a threshold where the outward paths that light could take no longer lead outward. Outside that threshold, light can still leave, though it may be bent and delayed. Inside it, the future points inward in a way that cannot be reversed. This is why the boundary has a special name, one that carries a quiet clarity. It is an event horizon. Not a wall, not a shell, but a horizon in the strict sense, a limit beyond which information does not return to us. For the simplest kind of black hole, one that is not spinning, the horizon's size is set by one thing only: mass. Increase the mass, and the horizon grows in a steady, predictable way. This is one of the strangest features of black holes, and also one of the most comforting. A larger mass does not create a denser horizon in the everyday sense. The density is not a property of the horizon at all. The horizon is geometry. Its scale is a length that can be written down and compared, if we know the mass. But this is where the mind can stumble, because bigger seems like it should always mean stronger. A small black hole, with a horizon only a few tens of kilometers across, can tear and stretch nearby matter with ferocious tides. A supermassive black hole, with a horizon larger than the orbit of a planet, can have gentler tidal forces at its edge. The boundary is larger, yet the experience near it may feel less violent. The word largest has to be protected from the instincts that come with it. Still, the horizon is one way of speaking about size, because it is tied cleanly to mass, and mass is the most stable handle we have. When people talk about the largest black holes, they almost always mean the greatest mass, not the widest shadow in the sky, not the largest region of influence. Mass, because mass is what shapes the surrounding orbits, what heats the nearby gas, what sets the tempo of the system around it. And yet, even mass, in this context, is not a thing you hold. It is not a pile of matter weighed on a scale. It is a parameter inferred from motion. We learn the mass of a black hole the way a sailor learns the presence of a submerged reef, by reading the flow of the water above it. Stars, gas clouds, and light itself become the moving surface that reveals the hidden shape below. This is why largest must be separated into different meanings, each true in its own way, each answering a slightly different question. There is the largest by horizon size, which is essentially the largest by mass for a non-spinning black hole. There is the largest by gravitational influence, which is not a boundary at all, but a gradient, a region where the black hole's pull begins to dominate the dance of a galaxy's core. And there is the largest by appearance, by the angular size of the dark shadow it can cast against a glowing background. That last one, the shadow, is not the horizon itself. It is a silhouette shaped by the paths light can take around the hole, a kind of lensing imprint. Its size depends on mass, yes, but also on distance and on how the surrounding material lights up. If a black hole were brought close enough, its shadow could loom large in the sky, even if its mass were modest compared to the giants in distant galaxies. If a truly enormous black hole sits very far away, its shadow could be tiny to our instruments, even though its horizon could swallow solar systems. So when we say, largest black hole we've ever measured, we must quietly decide whether we mean largest in the universe or largest in our measurements. The second phrase matters. It does not claim the universe has stopped. It admits our reach has edges. The event horizon is the cleanest theoretical boundary, but in practice the most measured boundary around black holes is often something else, the behavior of matter in orbit. When gas falls toward a black hole, it rarely falls straight in. It carries angular momentum, like a spinning coin that refuses to drop flat. That momentum spreads the inflowing material into a disk. The disk heats by friction and compression, and it can shine with extraordinary intensity. Not because the black hole emits light, but because the universe does not like waste. Gravitational energy, released as matter falls deeper, becomes heat, and heat becomes light. In those luminous systems, there is a natural scale that appears, the innermost stable circular orbit. This is the smallest orbit where matter can circle without plunging in. For a black hole that is not spinning, that orbit lies at a fixed multiple of the horizon radius. For a spinning black hole, it moves inward or outward, depending on the direction of the orbit relative to the spin. Here, the idea of size becomes layered. The horizon is one radius. The last stable orbit is another. The bright inner edge of the disk is yet another, and it shifts with the physics of gas and magnetic fields. If someone points to an image of a black hole system and speaks about how big it is, they may be pointing to the bright disk, or the jets, or the region of disturbed gas. Those features can extend far beyond the horizon. They can be vast. They can be brighter than the galaxy around them. But they are not the black hole itself. They are the black hole's environment, its influence made visible. So the documentary mind must learn a discipline to keep the black hole distinct from the stage it forces the universe to build around it. When astronomers announce a particularly massive black hole, what they have measured is typically a mass derived from the speed of orbiting stars or gas, or from the way a galaxy's central light flickers and echoes. Once the mass is known, the horizon size follows. That size can then be described in miles or kilometers, or compared to the orbit of Earth, or Jupiter, or beyond. But those comparisons are translations for our intuition. The measurement itself is not the comparison. The measurement is the mass. And even that mass comes with a particular humility. Every measurement is a statement about uncertainty. A black hole's mass is never known in perfect isolation, because the system around it is not silent. Stars tug on each other. Gas pressure adds forces beyond gravity. Magnetic fields twist and transport energy. The galaxy itself holds the black hole in a broader gravitational embrace. In many cases, we do not see individual orbits clearly enough to isolate the central mass without assumptions. So, measured often means constrained, pinned within a range by the best model that fits what we can observe. This is not a weakness. It is how knowledge looks at the edge of the possible. The phrase, "largest we've ever measured," carries another quiet implication, that we may encounter black holes larger still, but beyond our ability to confirm. In the far universe, a luminous quasar can suggest a central black hole of staggering mass. But the farther away we look, the more our methods depend on indirect clues and scaling relations, and the more our confidence rests on how well those relations hold across cosmic time. So, within the word largest, there is a boundary of human reach. There is the universe's true distribution of black hole masses, and then there is the subset that our instruments can weigh with enough confidence to put in a catalog. The title we are traveling under makes an honest promise, not the largest black hole that exists, but the largest one we have measured, and how we know. To understand that promise, it helps to hold two pictures at once, without letting them blur. One picture is geometric and austere, a black hole as a region where the future becomes inward, with a horizon that can be described by a radius set by mass and spin. In this picture, largest is a number that follows from a single parameter. It is a clean relationship between mass and length. The other picture is astronomical and lived in, a black hole as the anchor of a crowded system, surrounded by stars, dust, gas, and light, where measurement is done by watching how everything else moves. In this picture, largest is inferred from the choreography of a neighborhood. Both pictures are true, but they answer different emotional needs. The first tells us that the universe is lawful even at extremes. The second tells us why measurement is hard. Because we never observe the black hole alone. We observe it through the behavior it compels in everything around it. When a planet orbits a star, the system is gentle enough that we can ignore many small effects. When a star orbits a supermassive black hole in the center of a galaxy, the system is often chaotic in its details. There are many stars. There is gas. There is dust. There is sometimes a turbulent disk. The black hole may be feeding or quiet. The center may be shrouded. The orbits may be elongated and perturbed. Yet, within that complexity, gravity leaves a signature that is hard to hide. The faster the orbit at a given distance, the more mass must be enclosed. This is why, in practice, largest often begins as an argument about enclosed mass at small radii. A galaxy can have a dense cluster of stars in its center, contributing to the gravitational field. But only a compact object, something like a black hole, can pack a huge mass into a tiny region without shining like a cluster of ordinary stars. If the motion near the center is too fast to be explained by starlight, and if the mass must be concentrated into a volume that could not hold that many stars without collisions and disruption, the black hole becomes the simplest remaining answer. And once the mass is known, the horizon becomes a quiet afterthought, a radius that can be computed, a scale that can be spoken. The most important restraint, though, is not to let the horizon become a picture of a mouth. A black hole is not a predator. It does not pull harder because it is hungry. It bends space and time because mass and energy do that, and its horizon is simply the region where the bending becomes absolute in one direction. To call it largest is not to dramatize it, but to place it on a scale that is real and yet not directly visible. Even the word measured deserves this kind of patience. Measured does not mean photographed. Measured does not mean touched. Measured means derived from evidence with a method that can be described, repeated, challenged, improved. It means that if another team used the same observations and the same assumptions, they would land in the same neighborhood of results. It means there is a trail from data to conclusion, and that trail is the true object of study. That is why this chapter lingers on language. Before we talk about instruments, before we talk about discovery moments, before we talk about the largest known masses, we must clarify what we are even claiming. Otherwise, the mind fills in the gaps with the wrong kind of certainty. So, for the remainder of our journey, largest will be held in a careful way. It will mean the greatest mass that has been constrained strongly enough to be defended. It will imply a horizon size that follows from that mass. It will not be confused with the size of a galaxy or a jet or a glowing disk. And it will always carry the modest qualifier of our era, measured by us, from here, with the tools we have built, looking outward through layers of distance that soften and distort. With that definition in place, the black hole becomes measurable, not because it reveals itself, but because the universe cannot help but reveal it through motion. And because we are willing to admit how strange seeing becomes when the object has no surface at all. A useful way to keep the meaning of largest steady is to imagine that, in the center of a galaxy, there is a kind of invisible bookkeeping. Every star that swings past the center, every cloud of gas that drifts inward, every ribbon of light that curves on its way to us, is adding a line to that ledger. None of them needs to know what is there. They only respond. They speed up, slow down, turn, hesitate, or vanish. And from those responses, we reconstruct the simplest account that makes the whole ledger make sense. This is measurement in the presence of absence. It is not a single act, but a convergence. When mass is concentrated, gravity becomes steep. The steepness has a signature that does not depend on our metaphors. It depends on motion. If you know how far something is from the center and how fast it is moving, you can begin to infer the mass inside its path. The inference is older than telescopes. It is the same logic that allowed humanity to understand that the Earth moves around the Sun and not the other way around. The same logic that let us weigh planets we had never visited. But near a black hole, the scale becomes extraordinary, and the method must become careful. The first care is to decide what distance from the center even means, because the center can be hidden. In many galaxies, dust lanes and crowded starlight blur the core into a soft glow. In others, the nucleus flares with the light of gas falling inward, washing out detail. In some, the central region is so distant that the whole galaxy is a smudge, and the core is a single bright pixel. The universe rarely offers clean diagrams, so astronomers build distance out of geometry, and geometry out of light. They resolve what they can. They map the distribution of stars as a function of radius. They trace gas disks and measure how quickly they rotate. They watch bright spectral lines shift, because motion changes light in a reliable way. A star moving toward us shifts its light slightly bluer, and moving away shifts it redder. That shift, measured with patience, is velocity written into color. In a nearby galaxy, if individual stars can be tracked over years, the method becomes almost intimate. Their orbits are not guesses. They are drawn out by repeated observation, like handwriting slowly revealed. In the best cases, the mass at the center can be pinned down with a kind of inevitability. No cluster of normal stars could hide there because the required density would be unstable. No diffuse cloud could produce the same tight, rapid orbits. The mass must be enormous and compact. The black hole becomes less a speculative object and more a necessary conclusion. Yet those ideal cases are rare. Most of the time, we measure black hole mass at great distance in systems where we cannot follow a single star's dance. Instead, we read collective motion, the average behavior of many stars blurred together, or the rotation of gas in a disk whose structure we infer rather than resolve. The method remains the same in spirit, but more layered in practice. Each layer introduces uncertainty, and each uncertainty must be held honestly. This is where largest begins to involve a second meaning. Not only the largest mass, but the largest mass we can support with enough evidence to be confident. Sometimes the brightest systems suggest the largest black holes, but brightness is not mass. Brightness is activity. It tells us that matter is falling inward and releasing energy. A modest black hole can shine fiercely if it is being fed well. A truly massive black hole can be quiet if it has little to consume. So brightness can guide us to candidates, but it cannot crown a champion. To call a black hole largest measured, we need more than brilliance. We need constraints that tie the observed light and motion to the central mass in a way that does not depend on wishful interpretation. That is why, even before instruments enter the story, the word measured implies method, and method implies cross-checks. One cross-check is the relationship between a black hole and its host galaxy. Over decades, astronomers found that the mass of the central black hole correlates with properties of the galaxy's bulge, the central, rounded concentration of stars. The tighter and faster the bulge's stars move, the more massive the central black hole tends to be. This is not a rule carved into stone. It has scatter, but it offers a way to estimate black hole masses when direct methods are unavailable, and more importantly, it offers a way to test whether a proposed mass is plausible in context. A black hole that seems far too massive for its host galaxy raises questions, and those questions send observers back to the data. Yet, correlation is not measurement. It is a map that helps us not get lost, not a ruler we can trust blindly. The largest claims require something closer to a ruler, even if it is a ruler made of light. Another cross-check comes from time. In some galaxies, the central region flickers, not because the black hole changes, but because the environment near it is turbulent. Gas spirals inward, heats, brightens, dims. A flash of energy in the inner disk can illuminate gas farther out, and that gas can respond by glowing in characteristic spectral lines. The response is delayed because light takes time to travel. If the inner region brightens and the outer gas brightens later, the delay is a measure of distance. Distance expressed not in space, but in time. This technique, in its most refined form, allows astronomers to estimate the size of the region producing certain emission lines, and combined with the speed of the gas, again inferred from spectral line broadening, it can yield an estimate of the central mass. The logic is still gravitational. Faster motion at a given distance implies more enclosed mass. But now, distance is inferred from a light echo, and speed is inferred from how widely the light is smeared by motion. It is indirect, but disciplined. For very distant, very luminous objects, quasars blazing from the early universe, these time-based methods can become one of the few practical tools we have. We cannot resolve the central orbits. We cannot watch individual stars, but we can watch the system's own light telling time. Still, every such method is built on assumptions about geometry, about whether the gas is in a disk, a cloud, or an outflow, about whether the motions are mostly orbital or partly driven by winds. The best measurements are those where different methods agree, where one line of inference supports another, not by repetition, but by convergence from independent evidence. This is why the claim largest measured is never just a single number. It is a number carried by a network of reasoning. Now, inside that network, we return to the simplest and most austere measure of size, the scale of the event horizon. For a non-spinning black hole, the horizon radius grows in direct proportion to mass. If you double the mass, you double the radius. This is not a metaphor. It is a precise relationship in general relativity. That proportionality is one of the reasons mass is such a powerful concept here. Once you have it, you have a length scale that is not subjective. But real black holes can spin. Spin changes the horizon slightly, making it smaller in one direction and altering the structure of space around it. Spin also changes the location of the innermost stable orbit, which matters for the luminous environment. Yet even with spin, the mass remains the primary scale setter. The horizon's overall size still tracks mass, and the largest black holes by mass will have the largest horizons. So why not simply define largest as largest horizon? Because we do not measure horizons directly, at least not in most cases. We measure masses, and horizons are derived. Only in rare, extraordinary cases do we come close to seeing the shadow, the dark imprint against light that curves around a black hole. That shadow is not the event horizon, but it is directly tied to the geometry near it. When it can be measured, it offers a different kind of confirmation, a glimpse of curvature's effect on light itself, rather than on stars or gas. But a shadow's angular size depends on distance. A closer black hole with a smaller mass might cast a larger shadow on our sky than a more massive one far away. So again, we are forced to separate largest in the universe from largest in our sky. The shadow is a measure of apparent size, not intrinsic size. It is valuable, profound even, but it answers a different question. This is why a black hole can be largest in one sense and not in another. The largest shadow we can observe might belong to a relatively nearby supermassive black hole. The largest mass we've measured might belong to a distant galaxy cluster's heart, where the shadow is far too small for us to resolve. Both are true, and neither cancels the other, as long as the definitions remain quiet and precise. There is also the question of largest influence, and this one can be the most misleading if treated casually. Every black hole lives inside a larger gravitational system. In a galaxy, the stars and dark matter form a combined potential that dominates at large radii. The black hole dominates only near the center. The region where its gravity is the main sculptor is sometimes called its sphere of influence. Its size depends on the black hole's mass and on the typical speeds of stars in the galactic core. A more massive black hole generally has a larger sphere of influence, but that sphere is not a physical boundary. It is not a wall that divides one regime from another. It is a region where the black hole's presence becomes the simplest explanation for the motions seen. Outside that region, the galaxy's broader mass distribution matters more. So if one were to call a black hole largest because it has the greatest sphere of influence, one would be speaking partly about the black hole and partly about the host galaxy's structure. It is a mixed measure. Mass avoids that mixture. Mass belongs to the black hole in the most direct way we can assign. It is the quantity that defines the horizon size and sets the central gravitational scale. So the most disciplined meaning of largest returns us to mass. And yet, the very act of measuring mass leads us into the final subtlety of this chapter, the difference between what exists and what can be confirmed. The universe likely contains black holes larger than any we have measured. It would be surprising if it did not. Our measurements are limited by distance, by intervening dust, by the brightness of the environment, by the resolution of our instruments, by the time we can spend watching, and by the physics that makes some black holes quiet. A black hole can be massive and yet nearly invisible if it is not actively accreting matter. Without a bright disk or jet, it announces itself only through the motions of nearby stars and gas. In a distant galaxy, those motions become too small to resolve. The black hole becomes a silent center that we can only suspect. Even when a galaxy is active, the very brightness that helps us find it can hinder precision. A quasar's glare can drown the starlight of the host galaxy, making it harder to measure stellar motions. The environment that reveals the black hole can also conceal the details needed to weigh it. So, largest measured becomes a phrase that carries the shape of our instruments. It is the peak of a mountain range we can see, not the peak of the entire planet. This limitation is not discouraging. It is part of the documentary's deeper calm. The universe does not need to be fully known to be profoundly knowable in parts. Measurement is not a conquest. It is a conversation with what can be observed. And in that conversation, the word largest becomes less about dominance and more about relationship. A black hole's size, in the sense that matters here, is not a property we perceive directly. It is a property we infer from the way other things move and shine and change with time. That inference is anchored in a small set of physical principles. Gravity shapes motion. Motion imprints on light. Time delays reveal distance. And geometry can be reconstructed from patterns if you listen long enough. By the end of this first step in our journey, largest is no longer a vague superlative. It is a carefully placed marker at the intersection of theory and evidence. It means the greatest mass that our methods can support, with a horizon that follows, and with an honesty about the limits of confirmation. And in that honesty, there is a quiet strength, because it prepares the mind for what comes next. Not a spectacle, but a widening of what seeing can mean when the object has no surface and yet leaves its signature everywhere it is allowed to touch. The mind keeps a private map of reality, and it is drawn in familiar distances. A room, a street, a hill, the reach of an arm. The map is not made of numbers, but of expectations. If a sound is loud, it is close. If a thing is bright, it is near. If an object is large, it must be heavy. And if it is heavy, it must fall quickly. These are quiet rules, learned so early they feel like truth itself. They work well enough for a life spent among stones and trees and weather. But in the deep universe, those rules begin to drift. Light can be bright because it is ancient rather than near. A mass can be enormous, and yet the space around it can seem calm. A distance can be so large that the word far stops describing anything the body can imagine, and time, which feels like the one thing that never changes, begins to behave as a variable. Slower here, faster there, folded into motion and gravity. When people first hear the phrase black hole, the mind often reaches for the nearest picture it can find. It imagines a hole in the ground, a puncture, a tunnel, something removed from a surface. The picture is understandable, but it smuggles in a mistake. It treats space like a solid sheet that can be torn, and it treats the black hole like a place where matter falls out of the universe, as if down were an absolute direction. The cosmos does not give us that comfort. Down is local. It points toward mass, and mass can be arranged in ways that make the idea of a single downward direction meaningless. A black hole is not a pit in a floor. It is a region where the geometry of space and time is arranged so that future paths lead inward. It is not that matter falls through a hole. It is that inside a certain boundary, the options become fewer until there is only one. This subtle shift is already beyond intuition, because intuition expects space to be a stage and time to be a clock. We act as though space is where things happen, and time is what passes while they do. Yet, near the extremes of gravity, space and time become part of what happens. They are not separate from the drama. They are the fabric that changes shape. Even the idea of seeing begins to mislead us. In ordinary life, sight feels direct. Light leaves an object, enters the eye, and the world appears. Distance only weakens the signal. But in the universe, distance can do more than weaken. It can delay. It can bend. It can transform. A star's light can be shifted into red, not because the star is moving away in the familiar sense, but because space itself has expanded beneath the light as it traveled. A galaxy can be visible not as it is, but as it was when the Earth had no air. when the sun was still young, when nothing on this planet could have understood the word galaxy. So when we ask about the largest black hole we've ever measured, we are not just asking about size. We are asking what it means to know anything at all about a thing we cannot touch, cannot see directly, and may only observe as it once was, through a chain of distortions that are not errors, but features of the cosmos. The first limit, then, is scale. It is not that we cannot understand large numbers. We can recite them. We can write them down. The limit is that our inner sense of scale stops growing with the numbers. Past a certain point, 1,000,000 and 1,000,000,000 and 1,000,000,000,000 feel like the same blank expanse. The mind loses its footholds. In that blankness, it becomes tempting to rely on emotional shortcuts. Bigger becomes stranger. Farther becomes more dramatic. Older becomes more mysterious. But the universe is not obligated to match our feelings. A black hole 1,000 times more massive than another is not necessarily more violent to approach, and a distance 1,000 times larger does not necessarily feel different through the lens of a telescope. The same photons arrive, the same spectral lines shift. The data looks calm, even when the reality behind it is beyond the body's imagination. Another limit is our habit of treating time as a single river. We experience time as a flow that is shared. We meet another person and assume we occupy the same now. We move through the day as though there is one clock for everyone, one pace for existence. Yet the universe is woven differently. Time is local. It is affected by speed and gravity. Near a massive object, clocks tick differently than they do far away. At high speeds, time dilates. These are not poetic ideas. They are measured, repeated, woven into the way satellites keep time and the way particles decay. But intuition resists them because they do not match the body's experience. The body is not built to feel a fraction of a second stretching or compressing. So the mind tries to flatten the universe back into a single shared time, and in doing so, it loses the ability to picture what gravity really is. This matters for black holes because a black hole is, among other things, an extreme time machine. Not in the sense of traveling to the past, but in the sense that time near it behaves radically. Approaching the horizon, time, as seen by a distant observer, appears to slow. To the falling traveler, their own clock continues normally. These two descriptions feel contradictory until we accept that there is no universal clock to reconcile them. There are only local experiences of time, connected by the geometry of space-time. If the mind insists on one clock, it will insist on one story, and black holes do not permit that. A third limit is the way we imagine forces. In daily life, force is felt as push and pull. A hand pushes a door. Gravity pulls a stone. We imagine gravity as an invisible rope tied to mass. That picture is useful for throwing a ball. It becomes misleading when the rope begins to curve the stage itself. The deeper view, calmer, stranger, and more accurate, is that gravity is not simply something that acts within space. It is the way space and time are arranged. Objects move along the straightest possible paths available to them, and those paths appear curved because the geometry is curved. A planet orbiting a star is not being tugged sideways by a rope. It is following a geodesic, a straight path in a curved space-time. This is difficult for intuition because it requires the mind to treat geometry as active. We do not grow up watching space bend. We grow up watching objects bend. So we bring the wrong image to black holes and imagine gravity becoming infinitely strong at the horizon, as if the rope suddenly tightens. In reality, what becomes absolute is not force in the everyday sense, but the structure of possible futures. The horizon is not a place where gravity suddenly spikes like a cliff. For a sufficiently massive black hole, a crossing of the horizon can be locally uneventful. The laws of physics in the falling frame do not announce a boundary with a flash or a sound. The horizon is defined globally by what can and cannot reach faraway observers. Locally, it can feel like any other region of space. This is one of the quietest and most unsettling ideas in astronomy, that a boundary with such profound consequences does not have to look like anything. A fourth limit is our reliance on surfaces. We understand objects by their skins. A planet has a crust, a sea, clouds. A star has a photosphere, a visible layer. Even a gas cloud has an edge where density drops and the light changes. The mind likes surfaces because they let us say, here it is, here it ends. A black hole denies that comfort. Its defining boundary is not a surface you can scrape or heat or paint. It is a line in the behavior of light. It is not made of matter. It is made of inevitability. That makes the mind uneasy, because it forces us to accept that some of the universe's most important things are not things in the sense we are used to. So we substitute. We imagine the accretion disk as the black hole. We imagine the jets as the black hole. We imagine the bright center of a quasar as the black hole. These are understandable substitutions because they are what we can see, but they reverse the relationship. The light is not the object. The light is the trace of matter losing energy on the way down, the surroundings paying the price of being near a deep gravitational well. If we do not separate the object from the environment, our intuition will insist that the brightest black hole must be the biggest, or that a quiet black hole must be small. Both can be wrong. There is also a limit that hides inside language itself. The word whole suggests absence of matter. Yet black holes are not emptiness. They are mass compacted so intensely that their gravitational influence creates an escape boundary for light. The whole is not a gap in the universe. It is an extreme presence. Language points the wrong way, and intuition follows. And then there is the most subtle limit of all, our instinct to locate ourselves at the center of what is real. We see the night sky as a dome. We speak of distant objects as being out there, as if space were a room and we stood at its center. In fact, every observer carries their own center. Every point in the universe can be called central, depending on what you measure from it. The universe does not provide a privileged viewpoint. This matters because when we imagine distance, we imagine it in a single straight line outward from us. But observational distance is layered. Light can be delayed, it can be redshifted, it can be magnified by gravitational lensing, it can be dimmed by dust. Two objects with the same intrinsic size can appear different because the universe between us and them has shaped the light in different ways. So to speak of the largest black hole and mean something physical, we have to loosen the mind's grip on direct appearance. We have to accept that what looks large is not always large, and what looks small may be beyond comprehension in true size. The calm way through these limits is not to force the mind to picture everything, but to let the mind adopt new forms of intuition. Intuition built from relationships rather than images. Instead of picturing a black hole as a mouth, we picture it as a set of constraints on trajectories. Instead of picturing size as a boundary we could walk around, we picture size as the mass required to produce certain orbital speeds at certain distances. Instead of picturing time as a universal river, we picture time as something that can stretch and compress depending on where and how you move. These are not cold abstractions. They are replacements for misleading pictures, gentler and more faithful. And they prepare the listener for a deeper kind of seeing. The idea that we can know an invisible object by the harmony it imposes on its surroundings. That a black hole's mass can be read in the velocities of stars, in the temperature of gas, in the delay of echoes, in the curvature of light. That knowledge can be built without direct contact, without a photograph. without any surface at all. If there is a single lesson in this chapter, it is that the mind's first picture is rarely the best one. It is not wrong because it is simple. It is wrong because it is borrowed from a world where space is flat, time is shared, and objects are defined by what they show us. The universe beyond that world is still understandable, but it asks us to trade the comfort of direct intuition for something quieter. A trust in patterns, in constraints, in the slow logic of inference. There is a particular kind of calm that arrives when the mind stops demanding a picture. Not because pictures are useless, but because at extreme scales they become a trap. They invite the wrong expectations. They make the universe feel like an enlarged version of a room, with objects arranged inside it the way furniture is arranged on a floor. The cosmos is not that kind of place. Its most important features are not always visible, and its most decisive boundaries do not have to look like edges. So a more reliable form of intuition begins with a different habit. Not asking what something looks like, but asking what it changes. A black hole changes the timing of light. It changes the speeds of orbits. It changes the shape of a spectrum. It changes the distribution of heat around a center. It changes the geometry that determines which paths are possible and which are not. These changes are not visual metaphors. They are measurable shifts in relationships. And relationships are something the mind can hold without insisting on a literal image. This is where our limitations become useful, because they force us into a method that is naturally quiet. When the universe cannot be pictured, it can still be listened to. Consider the simple act of watching a star's light spread into a spectrum. To human perception, starlight is a single color, or perhaps a gentle variation. But in a spectrum, light becomes a line of information, a subtle code. Dark absorption lines appear where atoms have taken specific wavelengths. Those lines are steady enough that, when they move, we can interpret the motion as velocity. This is one of the great translations we have learned, that movement can be read in color. The mind can accept this more easily if it releases the demand for directness. Nothing in the spectrum feels like motion to the body. There is no wind of speed against the skin. There is only a shift in pattern. Yet, from that shift, we can infer how fast gas is orbiting in a distant galaxy. And from that speed, we can infer how much mass is drawing it inward. This is the kind of intuition the cosmos rewards, the intuition of indirect evidence, held steadily. But it must also contend with another of our instincts, the instinct to treat measurement as certainty. In daily life, measurement feels clean. A length of wood is a length of wood. A clock's face shows a time. A scale shows a weight. The errors are small compared to the things being measured. In astronomy, measurement often works the other way. The uncertainties can be as large as the signals. A distant galaxy can be partly obscured. The motions of gas can be blended by resolution limits. Light can be stretched by expansion. Time can be blurred by irregular flickering. The data arrives with softness at the edges. So, measured becomes an art of working with softness without pretending it is sharp. This is another cognitive limit. We crave crisp boundaries in a world that rarely offers them. We want a black hole to be either the largest or not. We want the mass to be exact. But the universe gives us distributions, probability, ranges. It gives us confidence intervals, not finality. To be comfortable in this terrain, the mind has to learn a new kind of satisfaction. Satisfaction with strong constraints rather than perfect answers. Satisfaction with knowing what must be true within a range. This matters for black holes because the phrase largest measured is always provisional. Not provisional in a weak sense, as if the knowledge is unstable, but provisional in the honest sense that future observations could refine, re-rank, or replace. The cosmos is not a list that we have completed. It is a horizon we keep walking toward. There is also a deeper limit that shows up whenever we try to imagine a black hole's interior. The mind wants a place. It wants a location where the mass is. It wants to know what lies inside. But the interior is not simply hidden by darkness. It is hidden by causal structure. The horizon is not a curtain that could be pulled aside. It is a boundary beyond which information cannot reach us. To ask what is inside in the same way we ask what is inside a cave is to apply the wrong category. That does not mean the question is meaningless. It means the question belongs to theory in a way that cannot be completed by observation. The mind, however, prefers questions that can be closed with a view, so it pushes again and again for a picture. This is why black holes become a kind of mirror for human cognition. They force a confrontation with the distinction between what can be inferred and what can be seen. They expose the subtle ways we confuse the two. Even the idea of center becomes slippery. In a rotating system, the center is not necessarily a point you could mark with a pin. In turbulent accretion disks, matter swirls, heats, and magnetically reconnects. Bright regions flare and dim. The brightest spot is not always the center of mass. The mind wants the brightest spot to be the most important, but the universe often places the important thing in shadow, and the visible activity in the surrounding layers. This is why careful astronomy is always an argument against our first impressions. The mind also carries a deeply human assumption about emptiness, that if something is empty, it is simple. Space feels empty to the senses. A clear night sky feels like nothing between here and the stars. Yet the emptiness between galaxies contains radiation, tenuous gas, magnetic fields, and a geometry shaped by the expansion of the universe. Light passing through it can be lensed, reddened, delayed, scattered, absorbed. The path is not a straight line in a neutral void. So when we try to measure faraway black holes, we are measuring through an environment that is not inert. The measurement is a conversation not only with the black hole's neighborhood, but with everything between us and it. This adds another layer to our limited intuition. We tend to imagine measurement as a direct line, an arrow from observer to object. In reality, measurement is a chain. Every link in the chain can alter what reaches us. Good science is the careful accounting of those links. And yet, despite all of these limits, the universe gives us a gift. The laws are consistent. The same gravity that shapes the orbit of the moon shapes the orbit of stars around a galactic center. The same Doppler effect that changes the pitch of a passing car changes the wavelengths of light from moving gas. The same principle that lets us infer a hidden planet from a star's wobble lets us infer a hidden black hole from the motions of a galaxy's core. Our intuition fails at scale, but our reasoning does not have to. We can build a ladder. The rungs of that ladder are not pictures, they are correspondences. If motion implies mass here, it implies mass there. If light carries timing information here, it carries timing information there. If geometry bends paths here, it bends paths there. Each correspondence extends our reach. This is why the story of measuring the largest black hole is not primarily a story about an object. It is a story about the mind adapting its own tools. The adaptation is quiet. It does not feel like revelation. It feels like patience. The willingness to accept that a black hole may be best understood not as a devouring thing, but as a constraint on futures. Not as darkness, but as geometry. Not as an image, but as a set of measurable relationships. And as the mind adopts that patience, something else shifts as well. The emotional tone of the unknown. At first, the unknown can feel like a threat, because the mind equates uncertainty with danger. But in astronomy, uncertainty is often simply distance. It is the cost of looking far. It is not malevolent. It is the texture of the cosmos at the edge of our instruments. When we accept that, the unknown becomes less sharp, less alarming, and more like a landscape fading into mist. Still real, still structured, but not yet resolved. This is a sleep-friendly kind of awe. Awe that does not spike the pulse, but settles into the recognition that reality is larger than the body's instincts. The largest measured black holes sit at the intersection of all these themes. Their size cannot be felt, their boundaries cannot be touched, their presence is often inferred from the behavior of things that glow, move, and flicker around a hidden center. The distances involved mean we are often seeing them as they were, not as they are. The measurements are therefore not declarations of absolute truth, but careful statements about what the evidence compels us to believe. To hold that without anxiety, the mind must become comfortable with layered knowing. It must accept that we can be confident without being absolute, that we can measure without seeing, that we can know a mass without finding a surface, that we can speak about largest while admitting the universe may contain larger still, beyond our present reach. When that comfort settles in, a final limit becomes visible, and it is perhaps the most human one, the limit of imagining ourselves outside the universe, looking in. We are not outside. We are embedded. Our telescopes are made of matter shaped by the same physics we study. Our clocks are subject to the same relativistic rules. Our measurements are made from within the flow of cosmic time, on a small planet, around an ordinary star, in one galaxy among many. To measure a black hole across the universe is, in a sense, the universe measuring itself through us. The information travels, the patterns arrive, and the mind, limited, quiet, persistent, finds a way to translate. And that translation is the true achievement. It is the reason we can speak, with restraint, about the largest black hole we've ever measured. Not because we have conquered the darkness, but because we have learned to read its imprint without insisting it look familiar. The universe rarely offers its deepest objects in plain sight. It offers them indirectly, as effects that appear in places where nothing obvious should be causing them. A star that moves too fast around an empty-looking center. A disk of gas that glows with heat that cannot be explained by starlight alone. A beam of radiation that rises and falls with a rhythm that seems to come from a space too small to resolve. The unseen announces itself through patterns, and the patterns become our language. To measure what cannot be seen, the first requirement is not a telescope. It is a definition of what counts as evidence. In the world of ordinary objects, evidence is often visual. We trust what we can outline and photograph. But in astronomy, the most reliable evidence is often dynamical. It is the behavior of motion under gravity. Gravity is patient. It works over long times, across vast distances, and it leaves signatures that do not depend on our mood, our culture, or our expectations. If something is present, massive enough, and concentrated enough, the surrounding universe cannot help but respond. That response begins with a simple truth. Motion carries information about mass. If an object moves in a circle, something is holding it in that curve. If the curve is stable, the inward pull is balanced by the object's tendency to fly outward. The faster the orbit, the stronger the inward pull must be. And the stronger the pull, the more mass must be enclosed. This relationship is as old as the first understanding of planetary motion, yet its power does not weaken at the edge of galaxies. It scales upward with calm consistency. So the foundations of measuring a black hole begin not with the black hole, but with orbit. A star orbiting a galaxy's center is a moving test particle. A cloud of gas rotating in a disk is a collection of moving test particles. Even light, in its own way, is a test particle, following the geometry of spacetime. We do not have to touch the central mass. We have to watch how these tracers move, and then ask what arrangement of mass could produce that motion. This is where the idea of enclosed mass becomes essential. At any given radius, the speed of orbit tells you how much mass lies inside that radius. It does not immediately tell you how that mass is distributed within. It does not immediately tell you whether the mass is a black hole or a dense cluster of stars or something more exotic. It tells you a minimum requirement. There must be enough mass within that region to bend the path into the observed curve. The distinction is subtle but important. The universe often lets us measure mass before it lets us identify what the mass is made of. In many cases, the mass comes first as a gravitational demand, and only later, through additional evidence, does it become a black hole. For black holes, the additional evidence is compactness. A star cluster can be massive, but it has limits. Pack too much mass into too small a volume of normal stars, and the cluster becomes unstable. Stars collide, exchange energy, merge, explode, or are ejected. A stable configuration requires space. A black hole, by contrast, is a solution to compactness. It is a way for mass to be concentrated beyond the point where ordinary matter can remain in equilibrium. So the foundations involve a two-part inference. First the mass, then the compactness. If the required mass is so large and the required volume so small that no stable cluster of ordinary objects could hide there, the black hole becomes not a dramatic guess, but the simplest remaining explanation. There is another foundation that makes this possible: the translation between motion and light. We cannot usually watch stars in distant galactic centers trace their paths with the eye. We cannot follow the curve directly. But motion imprints itself on light in ways that physics keeps steady. When a star moves toward us, its spectral lines shift slightly. When it moves away, they shift the other way. Gas moving at different speeds can broaden emission lines, smearing them into wider features. A rotating disk can show one side shifted toward blue and the other toward red. These shifts are small, but they are measurable with careful instruments, and once measured, they become velocities, numbers that can be fed into gravitational reasoning. So the foundation is not seeing in the everyday sense. It is converting light into a record of speed. This is why spectroscopy sits at the heart of measuring the unseen. It is the craft of turning a faint line into a story about motion. But motion alone is not enough. We also need scale. We need distance. In the familiar world, distance can be paced out or measured with a tape. In astronomy, distance is another form of inference. We build it using standard candles, standard rulers, geometric parallax, and redshift relationships. Each method has its domain of reliability. Each carries uncertainty. Yet, without distance, velocities cannot become masses in physical units. A speed is not enough. We need to know the size of the orbit, the radius at which that speed occurs. So measuring a black hole mass is always an act of triangulation between three things: speed, scale, and model. The model is not optional. It is the bridge between observation and mass. It tells us, for example, whether we are interpreting the motion as orbital rotation or as turbulent outflow. It tells us whether a disk is edge-on or face-on, because inclination changes the velocities we infer from line shifts. It tells us how pressure, magnetic fields, and radiation forces might slightly alter a pure gravitational orbit. The best foundations are those that keep the model minimal and testable. We cannot escape interpretation, but we can keep it honest by using methods where geometry can be constrained, where multiple lines of evidence converge, where alternative explanations can be ruled out. This brings us to another key concept: timescale. A system's characteristic time is often a clue to its size. If something changes quickly, the region responsible cannot be too large, because signals cannot cross large distances instantaneously. This is not philosophy. It is causality. Light itself sets a speed limit. If brightness from a region doubles in an hour, then the region producing that change must be no larger than the distance light can travel in an hour. Otherwise, different parts of it could not coordinate the change. In black hole systems, this becomes a powerful constraint. The inner accretion flow can flicker, hot spots can orbit, X-ray emission can rise and fall. These variations carry an imprint of proximity to the central mass. The closer the emitting material is to the black hole, the shorter the characteristic timescales can be. So timing becomes another ruler, one made of the universe's own speed limit. And when timing is combined with velocity, when we can say, this gas moves at roughly this speed and it lies roughly at this distance, mass begins to emerge with a steadiness that does not depend on direct imagery. There is also the foundation provided by relativity itself, the recognition that gravity affects light, not just matter. Light passing near a massive object is deflected, its path curves, its travel time is altered, its frequency can shift in a gravitational field. These effects are not only theoretical, they are measured in many contexts, from the sun's influence on starlight during eclipses to the lensing of galaxies by clusters of mass. Near black holes, the bending can be extreme. Light can orbit, looping around before escaping. A bright ring can form not because the black hole emits, but because space guides the light into paths that linger. A shadow can appear not because there is a dark object blocking light, like a solid disk, but because certain paths lead inward and do not return. So relativity provides a foundation for seeing a black hole's imprint on light. It also provides a foundation for interpreting velocities near deep gravitational wells, where Newton's approximations begin to slip. Yet there is an important restraint here. Most mass measurements of black holes do not require full relativistic modeling. They rely on gravity's broader, calmer effects in regions outside the immediate horizon. The reason is practical. Our best tracers often live at distances where Newtonian dynamics approximates the motion well enough, and where uncertainties from astrophysical complexity outweigh the subtle relativistic corrections. This restraint is part of the sleep-friendly honesty of the subject. The universe is extreme, but our methods are often grounded in simple relationships, applied carefully. Still, the closer we attempt to measure, the more relativity becomes unavoidable. When we interpret the broadening of lines from very fast-moving gas close to a black hole, we must consider not only Doppler shifts, but gravitational redshift. When we interpret timing from regions near the innermost orbits, we must consider how time itself is shaped by gravity and speed. So another foundation emerges, the idea that measurement is layered by radius. Far from the black hole, the galaxy dominates, and the black hole is a subtle perturbation. Closer in, the black hole dominates and the galaxy recedes. Very close in, the details of space-time matter. Our observational methods, too, change with radius. Stellar motions can be tracked at one scale, gas dynamics at another, reverberation and variability at another, and direct imaging of shadows, rarely, at the most extreme observational frontier. Yet underneath these different methods lies the same steady spine. Mass reveals itself through how it shapes motion and light. Now, if all of this sounds like an accumulation of tools, it is. But the true foundation is simpler. We assume the universe is consistent enough that these tools remain valid. We assume gravity works the same in other galaxies as it does here. We assume light obeys the same physical rules across cosmic distances. We assume that the spectral lines of hydrogen and iron mean the same thing whether they form near Earth or near the center of a quasar billions of light years away. Without that assumption, there is no astronomy at all, only isolated impressions. The fact that astronomy works, quietly, repeatedly, is evidence that the assumption holds. And from that evidence, we gain permission to do something that would otherwise seem impossible: to weigh an invisible object at the center of a distant galaxy using nothing but faint light and careful reasoning. This chapter's foundations are not dramatic. They do not require a single grand leap. They require a willingness to accept that knowledge can be built from constraints, that certainty can be replaced by convergence, and that measurement at cosmic scale is an act of translation. Light arrives at our instruments as a thin stream. We spread it, record it, time it, compare it. We extract motion from color, scale from geometry, size from time, mass from orbit. And in doing so, we begin to make the unseen legible. A black hole is often described as if it were a single object, alone in darkness. But the universe does not present it that way. What we meet in observation is always a system: stars that drift and turn, gas that swirls and warms, dust that obscures and reddens, light that flickers with a rhythm shaped by forces we cannot see. The scientific foundations become most real when they are applied to this living complexity, when we take the clean ideas of mass, orbit, and light and set them down inside an environment that is restless. The first thing that environment teaches is humility about geometry. A rotating disk around a black hole can be tilted. If it is face-on, the gas moves mostly sideways relative to us, and the Doppler shifts appear small. If it is edge-on, one side rushes toward us and the other away, and the shifts become obvious. The same system can look dramatically different depending on orientation. So measurement begins with asking not only what is moving, but how the motion is angled to our line of sight. This is why, when astronomers infer a velocity from a spectral line, they are rarely satisfied with a single number. They look for complementary clues: the shape of the disk in images, the polarization of light, the presence of obscuring structures that suggest certain orientations, the way variability is seen through intervening gas. The goal is to constrain inclination, because without it, velocity can be underestimated and mass can be misjudged. Another lesson is that not all motion is orbit. Gas near a black hole can be driven outward by radiation pressure. It can be launched in winds. It can fall inward in streams that are not circular. It can be stirred by turbulence and magnetic fields. If we mistake an outflow for rotation, we could infer a mass that is not real. So a foundation of measuring the unseen is the discipline of distinguishing gravitational motion from other kinds of motion. This is done not by intuition, but by pattern. Rotating disks often produce characteristic double-peaked line profiles, where one peak corresponds to gas moving toward us and the other to gas moving away. Outflows often produce asymmetric features, absorption on one side of the spectrum, or signatures that change with viewing angle. Over time, rotation can produce stable repeating patterns. Winds can be episodic and directionally biased. The universe offers hints, but only if we treat the data as a language rather than a picture. Timing, too, becomes more nuanced when it meets reality. A simple causality argument says a region that varies quickly must be small, but in an accreting system, variability can be layered. Small regions vary quickly. Larger regions respond more slowly, and the observed light may be a mixture. A flare in the inner disk might illuminate a surrounding region and create a delayed response, but the response can be smeared if the surrounding region is extended, or if light takes multiple paths due to scattering and geometry. So a measured time delay is often not a single distance, but a weighted average over a three-dimensional structure. This is why reverberation methods, using light echoes to infer the size of emitting regions, are powerful but subtle. They rely on careful statistical treatment of light curves, on models of how emission line regions respond, and on long-term monitoring that can separate true delays from coincidence. The foundation here is not only physics, but patience, the willingness to watch a distant object long enough to learn its rhythms. And then there is the question of what exactly is being measured. When we talk about black hole mass, we often mean the mass enclosed within a very small region, inferred from the motions of tracers. But in a galactic nucleus, there can be a dense cluster of stars, gas, and dark matter as well. Some of that mass is distributed, not concentrated at a point. If our tracers are not close enough to the center, the inferred mass can include contributions from this surrounding material. To isolate the black hole, we must probe deep enough into the gravitational potential that the black hole dominates. This is where resolution becomes destiny. The finest measurements are made when we can resolve the black hole's sphere of influence, when our instruments can distinguish motions at radii small enough that the central mass overwhelms the background. Without that resolution, we can still estimate, but the uncertainty grows, and the measurement becomes more model-dependent. So another foundation emerges. The idea that measurement quality is not only about sensitivity to faint light, but about sharpness in space. Sharpness is hard because galaxies are far. The atmosphere blurs images. Even in space, telescopes have finite apertures. Yet astronomy has developed ways to push against this limit: adaptive optics, interferometry, careful calibration. Each improvement in resolution effectively brings the universe closer, not by moving us, but by refining the points of light into separable structures. Now, beneath these practical concerns lies an even deeper foundation: the distinction between mass and brightness. The universe is full of bright things that are not massive, and massive things that are not bright. Stars shine because they fuse. Black holes do not. Gas can shine brightly when heated in a disk, but that brightness is a function of accretion rate and efficiency, not mass alone. A black hole can be massive and quiet, or smaller and radiant. So when we measure, we train ourselves to treat light not as mass, but as a messenger. Light tells us about temperature, composition, speed, geometry, and time variability. Mass must be inferred through the effect that mass has on those properties. If we confuse the messenger with the message, we will overestimate the role of the visible and underestimate the role of the hidden. This becomes especially important in the most luminous systems, the quasars. Quasars can outshine their host galaxies, making them easier to spot across great distances. Yet their glare can also erase the very starlight we would use to measure the motions of the host. So the methods shift. We rely more on gas dynamics and reverberation. We rely on scaling relationships that connect observable properties, like the width of emission lines and the brightness of the continuum, to estimated masses. These scaling relationships are built on foundations laid closer to home, in systems where multiple methods can be applied and cross-checked. A nearby active galaxy might allow both reverberation mapping and stellar dynamical measurements, providing a calibration. Once calibrated, the relationship can be applied to more distant objects where only reverberation-style clues are available. This is one of the quiet ways science extends itself. It builds bridges from the near and measurable to the far and inferred. But bridges have tolerances. The farther we go, the more we must ask whether the calibration holds under different conditions, different cosmic eras, different environments, different feeding rates. This is why the largest mass claims are often accompanied by careful language about uncertainty and method, because the foundation is strong, but not infinite. There is another relativistic foundation worth holding gently here: gravitational redshift and the deepening of time near massive objects. In some spectra, The shapes of lines from the inner regions of accretion disks show asymmetries that reflect both high orbital speeds and the redshifting effects of gravity. The light from the side of the disk moving toward us can be boosted, while light from the far side is diminished and shifted. The line becomes skewed, broadened, and extended to lower energies. These are not arbitrary distortions. They can be modeled in detail, and the models can suggest how close the emitting material is to the black hole, and even hints about spin. This is not always used for mass measurement directly, but it reinforces the foundational picture. The unseen object is shaping light in predictable ways, and those ways carry information about the depth of the gravitational well. The same is true for the bending of light itself. When a massive object sits between us and a distant light source, it can act as a lens. It can magnify the source, create multiple images, stretch it into arcs. In some cases, lensing can magnify a quasar, making it visible when it might otherwise be too faint. Yet lensing can also complicate measurement, because the observed brightness is altered by the lens, and brightness can enter mass estimates in scaling relationships. So another foundation appears. We must account for the universe between us and the object, not just the object itself. In this way, measuring black holes becomes a demonstration of the interconnectedness of cosmic phenomena. Expansion affects redshift, dust affects spectra, lensing affects brightness, instrument resolution affects dynamics. The black hole itself remains unseen, but its measurement depends on a web of physical processes that we can model and constrain. What holds this web together is the principle of consistency. If a proposed black hole mass implies certain orbital speeds, those speeds should match spectral shifts. If it implies a certain size for a reverberating region, that size should match observed delays. If it implies a certain relationship with the host galaxy's stellar velocity dispersion, that relationship should not be wildly violated without a reason. If different methods disagree, the disagreement is not an embarrassment. It is a clue that something in the assumptions needs attention. This is perhaps the deepest scientific foundation. Measurement is not a single path, but a set of independent paths that should converge on the same mountain. And convergence is what lets us speak with confidence, even in the absence of direct sight. When enough independent constraints point toward a mass, when stellar motions, gas dynamics, timing, and host galaxy properties are consistent, then the unseen becomes measurable in a way that is calm and firm. The black hole remains dark, but the evidence around it becomes bright with meaning. This is how the universe allows us to know things without seeing them. It offers us an economy of effects. It does not reveal the object directly, but it reveals what the object must be doing to everything nearby. And because the laws are steady, those effects can be translated into mass, and mass into size, and size into a place on our maps of the cosmos. By the time these foundations are in place, measurement no longer feels like a bold claim. It feels like a careful accumulation, a set of inferences that could be challenged but not easily dismissed, because they are not built on one observation alone, but on the universe repeating its rules in many forms. And in that repetition, we find the quiet power to weigh what cannot be seen. Night after night, the sky offers the same outward calm. The stars hold their places. The galaxies remain faint and distant. Nothing in the view suggests that some of the universe's heaviest objects are hidden at the centers of those soft smudges of light. And yet, when we begin to measure carefully, the calm becomes structured. Motions that once looked like random drift begin to reveal a central rule. The unseen appears not as a shape, but as a pattern that repeats wherever gravity has had enough time to organize matter. Knowing, in astronomy, rarely arrives as a single moment of sight. It arrives as a set of observations that lock together, each one reducing the space of possible explanations until only one remains practical. For black holes, the turning point was not simply the realization that they might exist. It was the moment they became measurable in a way that could be defended. At first, the idea lived mostly in equations and in the consequences of those equations. If general relativity allowed a region from which light could not escape, then nature might build such regions. But the sky did not label them. There was no simple signature that said, "Here is an event horizon." The early hints came from energetic sources, objects that shone too fiercely to be explained by ordinary stars. There were quasars, bright points at vast distances, feeding on something not directly seen. There were X-ray sources, variable and intense, suggesting compact engines. The universe seemed to contain power plants that fit in small volumes and yet outshone whole galaxies. These hints were persuasive, but they were not yet a measurement of an object. They were a measurement of behavior. The method that made black holes feel real in a new way was the method of motion. In nearby galaxies, the central regions are crowded and difficult, but not impossible. With sharp enough instruments, the light from individual stars can be separated from the general glow. Their positions can be tracked. Their spectral lines can be measured. In the Milky Way, this became the clearest example of how we know without seeing. Stars near the galactic center traced tight, fast orbits around a point that was dark. Not dark because it was hidden behind dust alone, but dark because it did not shine like any cluster of ordinary matter could. Over years, those stellar paths became undeniable. They were not vague drifts. They were closed curves, repeating in a gravity that demanded a compact mass of millions of suns. If the mass had been distributed among many stars, the cluster would have produced light, and the orbits would have been altered by the cluster's internal dynamics. The most stable explanation was a single, compact object. The black hole was no longer a theoretical possibility. It was a gravitational necessity. This was one turning point. Black holes could be weighed. But the documentary title speaks of the largest black hole we've ever measured, and the largest ones do not live in our own neighborhood. They live in distant galaxies, often in environments where individual stars cannot be tracked with the same intimacy. So the methods broaden. The turning point becomes not a single technique, but an entire shift in observational capability. The ability to resolve motions near galaxy centers, and the ability to interpret the light of active nuclei with enough discipline to extract mass. In many galaxies, the central mass is inferred from the average motion of stars. When starlight from the core is dispersed into a spectrum, the absorption lines appear broadened because different stars are moving at different speeds along our line of sight. That broadening can be quantified as a velocity dispersion, a measure of how fast the stars are swarming within the central gravitational field. Combine that with a model of how starlight is distributed in space, and you can infer how much mass is required to hold that swarm together. This is not a perfectly clean method. The orbits of stars are not all circular. They can be elongated. They can be preferentially aligned. The galaxy can be triaxial rather than spherical. The starlight you see is only part of the mass, because dark matter and faint stars contribute. Yet, with careful modeling, and with data of sufficient resolution, the black hole's contribution can be separated from the broader galaxies. The key is resolving the region where the black hole dominates. Gas offers another method, sometimes cleaner, sometimes more treacherous. In some galaxies, there are orderly disks of gas rotating around the center. Gas tends to settle into a plane. If the disk is relatively calm, its rotation curve can be measured, and the mass required to produce that rotation can be inferred. But gas is sensitive to more than gravity. Pressure gradients, turbulence, and magnetic fields can add forces that mimic or mask gravitational motion. So, gas dynamical measurements often require additional checks, comparing different emission lines, mapping the disk's geometry, looking for signs of shocks or outflows. Where these checks hold, gas can act like a luminous set of test particles, outlining the gravitational potential with a clarity starlight sometimes lacks. Then there are the most distant, luminous systems, where the black hole announces itself by feeding. Active galactic nuclei are bright not because the black hole shines, but because matter falls inward and releases energy. In these systems, the central region can be too small to resolve, yet it leaves time signatures. The brightness changes. Emission lines respond with delays. The widths of those lines reveal velocities. And from the combination of velocity and a time-derived scale, a mass estimate can be made. This is the world of reverberation mapping and single-epoch mass estimators, built on the same core logic but applied through different observational constraints. It is one of the reasons black hole catalogs extend so far into the universe. Timing and spectroscopy can travel farther than spatial resolution. But this brings us to the second half of the chapter's promise: remaining uncertainty. In science, uncertainty is not ignorance, it is a measured part of the claim. It tells you how strongly the evidence constrains the answer. For black holes, uncertainties grow with distance and with the complexity of the environment. They also grow with the indirectness of the method. A stellar orbit measurement near the Milky Way's center is anchored in geometry and repeated observation. Its uncertainties can be reduced by watching longer, by improving astrometric precision, by refining distance measurements to the galactic center. A reverberation-based estimate of a distant quasar's black hole mass is anchored in empirical relationships calibrated from nearer systems, and in assumptions about the structure of the broad line region. Its uncertainties can be reduced too, but they are of a different kind. They depend on whether the calibration holds across cosmic time, on whether the geometry is similar, on whether the source is viewed from a typical angle or an unusual one. This does not make distant measurements weak, it makes them probabilistic. And when we speak about the largest black holes we have measured, we often speak about objects that sit at the edge of these probabilistic methods. Their masses are large enough that even the broad uncertainties do not erase the conclusion. Yet the ranking among the very largest can shift as methods improve, as new data arrives, as assumptions are tested. That is why the phrase, "largest we've ever measured," must always be heard with a soft implied clause. As of now, with current evidence, under the best supported models. A further layer of uncertainty comes from how black holes and galaxies evolve. The scaling relationships that link black hole mass to host galaxy properties are powerful, but they are not guaranteed to be identical in the early universe. Galaxies were younger, more gas-rich, more turbulent. Black holes may have grown rapidly in episodes that do not mirror the calmer growth seen in many nearby galaxies. So when we infer enormous masses for early quasars, we are also touching the boundary between observation and cosmic history. We see a quasar shining brightly at a great distance, meaning we see it at a time when the universe was young. The very existence of such a luminous engine raises deep questions about growth timescales and feeding mechanisms. But the measurement of its mass rests on indirect methods. This is a delicate situation. The object is real, the light is real, the physics is real, and yet the precise mass is surrounded by a wider halo of uncertainty than it would be nearby. In practice, astronomers treat this with careful layering of claims. They compare different emission lines. They correct for known biases. They seek independent checks through gravitational lensing studies, through host galaxy measurements when possible, through alternative modeling. Over time, the community builds consensus not by declaring certainty, but by narrowing the plausible range. The turning point, then, is not just one historic observation. It is the moment a culture of measurement emerges. A culture where black holes move from being suggested by extraordinary brightness to being constrained by ordinary gravity, where the methods are standardized enough that results can be compared across teams and telescopes. And as those methods matured, Another kind of observation quietly joined the story: the ability to approach the event horizon's influence on light itself. When very long baseline interferometry links radio telescopes across continents, it turns Earth into a single instrument with a resolving power far beyond any one dish. With that resolving power, the shadow of a black hole becomes a measurable feature, not the horizon itself, but a ring-like imprint created by light bending around a deep gravitational well. This is a different kind of knowing, a measurement tied directly to space-time geometry near the center, rather than to the motions of distant stars. Yet even this directness comes with its own uncertainties. The shadow's appearance depends on the structure of the emitting plasma around the black hole. It depends on calibration and imaging algorithms. It depends on how turbulent the accretion flow is during the observation. The black hole remains unseen, and the observed ring is a reconstruction of sparse data. Still, the measurement is a remarkable convergence, an independent line of evidence that mass and geometry match what other methods have inferred. When multiple kinds of observation converge, stellar dynamics, gas rotation, timing echoes, and horizon-scale imaging, the black hole's reality becomes less an idea and more a measured presence. And yet, the largest black holes we have measured are often too distant for horizon-scale imaging and too far for individual stellar orbits. They live in the regime where our strongest tools are collective dynamics and luminous signatures. This means the largest mass claims rest on the careful interpretation of systems that are not simple. So how do we know? We know because the universe allows cross-checks. A mass inferred from stellar velocity dispersions can be compared to a mass inferred from gas kinematics. A mass inferred from reverberation mapping can be compared to host galaxy properties. A mass implied by luminosity constraints can be checked against known limits of accretion physics. Different telescopes, different wavelengths, different methods can all be brought to bear on the same object. And when they agree within expected uncertainties, the mass estimate becomes not a guess, but a robust statement. This much mass must be there, concentrated near the center, or else the observed motions and light cannot be explained. The remaining uncertainty is not an embarrassment at the end of the story. It is part of the story's texture. It reminds us that measurement is bounded by the tools of a particular era, that the universe is larger than any catalog, that some of the largest black holes may be quiet, hidden in galaxies too distant or too dust-shrouded to yield clear dynamical measurements, that some objects we suspect today may be confirmed tomorrow, and some may be revised. In that sense, the largest black hole we've ever measured is not only an object. It is a marker of where our observational reach currently ends, and of how far inference can travel when it is anchored in consistent physics. The sky remains calm, the galaxies remain faint, but beneath that calm, the patterns hold, and from those patterns, we build a knowledge that does not require sight, only patient observation, careful modeling, and the willingness to let uncertainty be part of what we mean when we say we know.